to this IIS AI workshop. For those who just joined the online event, this is the IIS AI workshop for unlocking the power of artificial intelligence for real-world challenges. One part of the IIS annual theme called AI, Facts, Fictions, Futures. Now, let me introduce our next speaker, Professor Shih-Chii Liu. Professor Liu is a professor in the Faculty of Science at the University of Zurich. She co-directs the sensors group at the Institute of Neuroinformatics, University of Zurich, and ETH Zurich. Her research focus is on the design of low power, low latency, synchronous sparking sensors, bio-inspired computing circuit, event-driven deep learning network, and their use in neuromorphic artificial intelligence systems. Professor Liu is past chair of IEEE CS sensor systems and neural systems and applications technical committees. She is currently the chair of IEEE Swiss CS-ED Society and was general co-chair of the 2020 IEEE Artificial Intelligence for Circuit Systems Conference and IEEE SSCC Student Research Committee. Today, Professor Liu will share her expert experience on edge AI with neuromorphic sparking sensors. Please join me in welcoming Professor Shih-Chii Liu. Over to you.
Thank you. Thank you, Dr. Meng and also Dr. Rother for this warm welcome, and also to the Institute of Advanced Studies for hosting this event. And so I'll go ahead and share my screen. Oh, wait, sorry, I need to share it with sound. I have to do it one more time here. Yeah, okay. Can you see my screen?
Yes.
Yeah, perfect. Okay, let me go into present mode. And do you see my cursor also? If I move it?
Yes.
Yes, okay, perfect, thank you. Okay, so thanks everyone for being at this event. So I'm going to talk today about edge AI with neuromorphic spiking sensors. And this is the work that's going on in our group, Sensors Group, which I co-direct with Toby Delbrook. And so here on the front page, you see a couple of our spiking sensors. One is the auditory sensor, and the other is the dynamic vision sensor. And what you can see from the video is the kind of output that you get from this sensor, which is also called an event camera. And so I'm going to talk a bit about how the sensors are built and also how we apply them in edge AI applications. And what we're interested are, of course, are AI applications where you need real-time responses. And AI is a very big part of our lives. We use them, for example, for speech recognition. We talk to our smartphone if we want to look for the closest restaurant in town when we're away from home. And I heard a lot also about autonomous driving. So this is also a big application domain where real-time responses are needed. So you need to have networks that can do tasks like semantic segmentation, where you can look for pedestrians on the road so that the car will react fast enough so not to run over a person that's crossing the street. And so the way in which the tasks are solved in these applications is by using deep learning. And so nowadays, there's a whole zoology of networks that are used for solving this task, and they range from the much early days, simpler convolutional networks and recurrent neural networks to very sophisticated networks like residual networks, which are used in a lot of vision applications. And what I'm interested in is about the hardware that also runs underneath these networks so that we can build energy efficient systems. And so to run one of these networks, what you need to do is to do a lot of matrix vector multiplications. So for the hardware, you would need processing elements that can carry out these operations. So here's a picture of how you would have to multiply the weight matrix by an input vector to get the new output vector or hidden vector. And so the processing elements are needed to do this multiplication. And on top of that, you need memory. And memory is very important because you need to store the values of the input vector the elements of the weight matrix and also the elements of the output vector. And usually when you run these large networks, you typically run it on a very good GPU. So this is actually a much older GPU from NVIDIA, a 1080. And we usually look at the specs of the device because you don't want to start a simulation where you're using one of these networks and then you wait for weeks to get your answer. And so usually you'll pick a GPU device that has high throughput, and throughput here is specified in terms of the number of operations per second. And the other thing that we're concerned about is power, right? So in this case, for the 1080, it's spec'd at 100 watts if you're running a full load on this GPU. And power is of course something that we want to reduce, because if we use power, if you use a device that burns a lot of power, then you're going to generate a lot of heat, and there's a lot of side effects that happen. For example, the amount of carbon emissions that emitted by basically using the electrical power in order to run these devices. And so we're very concerned more with another kind of metric, which is called energy efficiency. So basically, for a certain throughput that you're getting, how much power do you need to get that throughput? And so what I'm going to show you next is a graph that shows the effective throughput, again measured in terms of operations per second. So going from 1 giga operations per second to 1 petal operations per second, and also the power consumption of that device. And what you see here on these lines is what we call effective energy efficiency. So that's the throughput divided by the power. So you get operations per joules. And so here's a line for all devices that come to 1 teraopt per joule. And here's another line for 1 gigaopt per joule. Of course, what you want to do to have a very high energy efficient devices is you want to come close to this line rather than this line. And so let us look at GTX 1080 again. And so it's spec'd to run at 9,000 gigaops per second at 100 watts. And here's a embedded device that also has a GPU, it's the Jetson Nano. And it's spec'd at 500 giga operations per second at 10 watts. And so you can see that they sit kind of in between these two lines. And what happens is the spec numbers that you get here is usually for running a batch of input samples. But if you want to use these devices for real-time operation, then what you're more concerned is how fast would these devices run if you have only a batch size of 1, right? So in this case, you can see the throughput of the GTX 180 drops from 9,000 gigaops per second down to 30 gigaops per second. And the same thing for the Jetson Nano, it drops down to 3 gigaops per second. So you can see that they're moving away from this curve of, or this line of 1 teraopt per joule downwards, which is where we don't want to be. And so for the kind of applications I'm talking about in the subsequent slides is that we're looking at devices that we can run on the edge. And usually when they talk about edge devices, they're talking about devices that will consume in watts, somewhere around 1 watt. And in fact, there's also a whole slew of devices that people are exploring where they will run only at millivolts. So basically trying to push the power numbers down to here while getting effectively the same number of operations per second per joule, per watt. Okay, and this is in the domain of Internet of Things, right? Which is a very big research domain. And if we look at how this whole domain is evolving, so let me just show a chart here. So if you look at the number of IoT devices that we have over the last 20 years, you can see that it's growing rapidly. And especially if you look into the domain where we're talking about edge devices, and you can see in fact, it's speculated by 2025, you're going to get a market, especially in voice activated devices, or what they also call the voice recognition market, is that you're going to get a market that increases by 2x or more than 2x, up to $27 billion of revenue. And so these are the kind of devices that you see around your home nowadays. So either it's through your home device, for example, your Amazon Echo, or one of the Google devices that you have at home, or something on the watch that you can talk to, or maybe a key tag that you can also talk to. And so all these devices here are basically something that we're really keen on exploring to see how we can use it with our neuromorphic technology. And so the specifications of these devices is that they're always on, and that you would do some sort of local processing on these devices, because when you have so many devices out there, the thing that you're concerned with is the data bandwidth. How are you going to transmit all the data you get on these devices up to the cloud so you can process them fast enough so that you can get the information or response that you want back again in a very short time. And so the best thing is if you can do some local processing on your device so that you can reduce the amount of data that you need to send up to the cloud. Of course, the other thing that people are concerned with is privacy, is not to have to send your data up to the cloud, but to do the processing on the device before, so that you don't have to send your own data up to the cloud. And real-time response, of course, is important here. And the last thing is it has to be small size, because you want to build very small portable devices. And all this places a constraint on the amount of power that the device should dissipate, and also the amount of memory that you can have on board. And so I want to talk briefly about the kind of things that we're concerned with when we think about the hardware that we need to use to run these networks that we use to solve edge task. And I just want to give you a little kind of an idea of what we're concerned with. So here's a network where we can compute the activation of a particular neuron by taking, say, the nonlinearity, a sigmoid, of the sum of the weighted inputs. Yeah. Okay, so first thing is, on the hardware, where are these activations stored? Well, they're going to be stored on, say, some on-chip memory. Yeah, so usually it's SRAM. And then the next thing is you need to get the weights. And usually with the weights, you would solve them off chip in DRAM. And so you have to fetch the weights onto the chip so that now you can have the two elements, the weights and the activations. And now this processing element would do the multiplication of the weights and the activations, sum this weighted inputs together, do the nonlinearity, and then give you the new output, the AI. And then you just repeat again for every neuron that you need to update. Now, one thing that's interesting that's been measured in a couple of places is that we also worry about the power that you use in each of these blocks, right? So it turns out that the processing element actually burns very little power. And what's costly is actually fetching numbers from the memory. So for example, when you fetch the activations from SRAM, it costs about 10x more power than what you burn the processing element block. And if you fetch the weights from DRAM, then you burn approximately 1000x more power than the power that you burn the processing elements. And so what that means is that whatever you do is you want to have your memory local to your processing element, and also you do not want to use a lot of memory for your network. And so the ways that you can increase the energy efficiency of your hardware is by first finding low memory footprint networks for the edge application that you're interested in. And if you have a low memory footprint network, then it reduces the required memory and power dissipation of the hardware. And the second thing is you want to reduce the precision of the weights and the activations, of course, while still guaranteeing high accuracy. And so there have been a lot of different approaches that have been taken to find this low memory footprint networks. And so, for example, for one of them is that you use transfer learning. So here's the original network that you train on a particular task. And then you use transfer learning to now teach, for this large network, to teach a much smaller network to solve the same task. And if you do that, then you can see that you need less memory to store the activations and also the weights when you compute the network. The other way is to do model compression. And one of the ways of doing model compression is by pruning the network. And so here you see an example where you can see that the neurons have been pruned away, right? So that you come to a reduced set of neurons and activations, and in weights that you need to solve the task, again, with a similar accuracy. And so with all these different methods, you can then reduce the original memory that you need, or the memory that you need for the original network, and then you can shrink the amount of memory that you need for supporting the smaller network and the pruned network. Again, this leads to a saving in terms of power, because as we show here once again, is if you look at the amount of power that you burn for the processing element, it's like up to 1000x, much lower than if you look at the power that you need to access the memory. So here's yet another way in which you can increase the energy efficiency of the system. So the other way is to reduce computes. And you can reduce computes by having methods that can sparsify the number of weight elements that you have in your weight matrix, and that also can guarantee you some high level or high percentage of activation sparsity. And this is something that you can usually do because the nonlinearity that used in the networks nowadays is the rectified linear unit, or ReLU. And so once you have a network that has either weight and activation or activation sparsity or both, then what you can do on the hardware is that first, when you have zero activations or the neuron has a zero output, you don't have to compute this matrix vector multiplication. You can just skip over it. And so here we show here in case one, where you skip with zero activations. So you have an input vector where you can see 3 of the elements are 0. And so what you can do then is for the weight matrix, you can basically ignore what's in these columns. And so essentially all you have to do are the computes needed for this input vector of 2, effectively 2 elements multiplied by the corresponding weights. The other way you can reduce computes is by skipping over the 0 weights. And so let's see the example over here. So again, you have an input vector. And if you have a weight matrix where most of the elements in here are 0, what you can do is that you can then reduce it basically to multiplying an input vector with a dimension of 2 multiplied by the corresponding weight elements. So in both cases, you can see that you can reduce the number of computes by quite a bit. Okay, so now I'm going to talk about how you can further reduce computes by taking inspiration from biology, right? The most amazing thing about our brain and also about insects is that you can do so much for so little power, right? So here's the example of a brain where the power that you burn is around 10 to 15 watts. And this is done using a distributed compute and memory architecture. And also underlying is an event-driven way of computing. I'm going to talk more about this. And on the other side over here you can see a bee that's exploring the flowers, looking for food. And again, it burns very little power, in a few tens of milliwatts. And this natural systems here can do so much. It can exhibit complex behaviors such as pattern recognition, navigation, and communication for that amount of power. And so we're very inspired about the principles that the brain uses in order to solve a whole bunch of complex tasks using such little power. And so let me then talk about how we are building this artificial event-driven computing systems. And so the idea here is to take inspiration from the retina, the cochlea, and also the brain, and to build a technology that imitates some of the principles that's used in this biological organs or elements. Okay, so first we have the spiking silicon retina that I'll talk about in a few seconds, a few minutes, and then also talk about the spiking silicon cochlea, and also the work that we do in a whole set of deep neural network architectures that are bio-inspired. And how we then put these pieces together, the neuromorphic spiking sensors along with this bio-inspired deep neural networks to solve some edge AI tasks. And in this, in our philosophy here, is that the inputs that you transmit from one module to another should be useful information. So you shouldn't just transfer, for example, samples of a camera, regardless of what's in the frame of the camera, of that image. And the second thing is you want to compute only when necessary while still achieving high task accuracy and precision. So let me first talk about the two sensors, the spiking silicon retina, also sometimes known as event camera, and also the spiking silicon cochlea. So this is our latest silicon retina or event camera. It's called the Davis, which stands for Dynamic and Active Pixel Vision Sensor. And it's mostly designed by Toby Dalbrook, the other co-director of the group, and his students. Also, there are a bunch of companies that have been selling this cameras. And so it's based on the functionality of the cells in the retina. And so here's a cross-section of the retina where you have the photoreceptors. And so we start off by imitating the function of a photoreceptor in silicon. So you can see the light falling in onto a photodiode is transduced into a current. Then we do a log compression, which is also what's done in the photoreceptors. Then we have the element that comes afterwards, which imitates the functionality of the bipolar cells. So what it does is it looks for changes or contrasts in the image. And this brightness or contrast changes are then compared against a threshold, and we generate events, which are spikes, right, that indicate constant brightness changes in the scene. And in this Davis pixel, we also have an additional readout scheme that also gives you the intensity of the input. And so this gives you like a picture that you would get from a camera on your smartphone. And so just to give an idea of what you get from the transient part of the retina, which is the dynamic vision sensor, is here's a video that shows what happens when you have a dot on a rotating disc. With the standard camera output, you will get a set of frames coming out that show where the dot is on the disc as the disc rotates. But what you get from the DVS is a stream of spikes from the pixels that see the dot as it crosses their location. And the nice thing about the DVS output is if the disc is not moving, then you still get frames from the standard camera that you have to process. From the DVS output, you get nothing. And with the DVS output, you can rotate the disc very fast and you don't get any motion blur. But in the standard camera output, you'll get motion blur because of the high speed of the movement. And so here's another example of what you get from the Davis. So again, as I said, you get two outputs. So one of them is a picture that looks like what you would get from your camera. And the other is the transient output that you get from the DVS. And so here's a camera that's mounted above the lobby in the hotel. Actually in the Capocacha Hotel, which is a place where we also have the Neuromorphic workshop every year. And so what you see here is when somebody moves, you then see the red and green dots that you saw before, and that's from the DVS output. And the red and green dots basically specify whether you're seeing on or off contrast event changes. Now, if you have the camera, you can see that you don't see smooth movement when somebody moves across the image. But from the DVS output, right, you can see basically the movement of the person. And you can even use the activity rate of this of spikes or events that come out from the camera to tell you when, here, for example, the spike indicates when somebody came into the picture. And then when somebody leaves the event, the rate drops. And you can also then use also the temporal information, the spikes that come out from the DVS output. So for example, here's a local spatial region where the spikes are coming across in a correlated way. And so you can use that to indicate that there is a person, and then you can then track this person as he moves across the scene. And this is something that's not easy to do with the frame output. Okay, so the next thing I want to talk about is the dynamic audio sensor or the spiking cochlea. And so here's the binaural cochlea, or the DAS as we call it. And it's got 64 frequency channels that range from 20 hertz to 20 kilohertz. One of our latest cochleas burn only 55 microwatts of power. So it's this little chip that sits here in this yellow box. And so with the cochlea, so it's basically this snail-like organ that if you unroll it, then inside you'll see a basilar membrane that's shaped in a way such that different places along the membrane will pick up different frequencies. And so if you measure the amount of displacement at these different locations along the membrane, you'll see that it's sensitive to a certain frequency ranging from around, say here, about 50 hertz to maybe 2 to 5 kilohertz. And so we can build this kind of transfer function in silicon. And this is what we have here in the binaural silicon cochlea. And so in this particular chip, we also built a simple model of the different hair cells, the inner hair cells, which transduce the displacement of the membrane into spikes that come out from the cochlea. And what you're going to see here in the set of 64 channels ranging from 20 hertz to 20 kilohertz, a set of spikes that come out when I talk. And if you don't talk, then you don't see spikes coming out. So I'm going to play a picture here. Yeah, so you can see the stream of spikes that come out as somebody says, for example, happy birthday. And now I show you yet another view, and this is from a different silicon cochlea. And now what we show here is the 64 channels, and here with time going into the screen. And again, when I play this movie, you can see the stream of spikes rolling across as someone speaks. And when no one is speaking or when there's no sound, then you don't get any spikes. And you can also look at the information that you get from the output spikes. So here is a spectrogram of a speech sentence of someone saying she had a dark suit in greasy wash water all year. And now you compare this input spectrogram with what we call the cochleogram, which is basically taking the spike outputs and then doing a spike count within 5 milliseconds, and then plotting again the spike responses when you say this particular sentence. And if you compare the two outputs, you can see that they have very similar pattern responses. And you can also take the spikes and reconstruct the sound. So here's the original sound.
She had your duck suit and greasy wash water all year.
And this is what we reconstruct from the spikes.
She had your duck suit and greasy wash water all year.
And so the spikes should carry enough information so you can solve an edge AI audio task later on. Okay, so now let's talk about some of the applications that we've done with our sensors. And in particular, we focus on those cases where we can save on power and computes while achieving real-time responses. And so I'll first show you two things that have been done with the DVS, but if you go onto YouTube, you'll see many more examples, especially if you look for videos by Toby Dalwood. And so this was a robot called the robot Goalie that was built at the Telluride Neuromorphic workshop back in 2003. And what you see here is the DVS is mounted looking down at a table. There's an arm here that blocks the ball as the person shoots the ball at the goal. And so let me play the video. So you can see that the motor responds extremely fast. In fact, you get a 3 millisecond reaction time with only a 4% load. And part of the reason why you can react so fast is because the data coming out from the retina is so sparse. So in this case here, you can see you only get events from the places where the ball is moving. And I'll show you another example, which is the case where the event cameras are now used on drones. Let me go forward. So here's a demonstration of how with the event camera, the drone can do a somersault, and this is done in the lab of Davida Scaramuza, which is the RPG group at the university. And so what you see here is the camera is looking at the square, and because the camera is has such short latency, you can see the square, even though the drone is flipping really fast. But if you look at the output of the standard camera, then you see kind of a blur, right? And so there are other places in which this event camera is being used, and one of them is also in autonomous driving. So I talk mostly now about the audio edge test that we're looking at. And so one thing is, when you look at the kind of tasks that you should do on the edge, is you have to do tasks that are not very complex, that require a small network. And this task include voice activity detection. So basically, when I do a keyword spotting, if I give a command to the home device, I don't want it to process all the speech that comes out from the background. So first, I want to run something that, or run a network that tells me when someone is speaking. So this way you can distinguish speech from background noise. And this is a voice activity detection task. And then once I detect a voice, then I look for the keyword, right? So this could be hello, right? And so then you have a separate network that does keyword spotting. And then once I have the keyword, once the keyword is detected, then I might want to do some speech enhancement. So I want to basically enhance the speech over the background noise. And so you can see this is kind of a hierarchical set of tasks that we engage. Instead of taking every sound sample that comes into the home device and processing up in the cloud, looking for the keyword, and also doing speech enhancement. And by doing this, then you can reduce the amount of power that you need to use up in the server. And so this way of doing hierarchical cascading saves you power. And from this chart over here, you can see that the voice activity detector network burns the least amount of power. And what you can do then is you can tag on another task. Afterwards, once the voice is detected, you can do speaker verification, you can do speech enhancement, and then also keyword spotting up to speech recognition. And so by doing this, you can reduce the power by 1000x, right? And so that's why we're very interested in how you can build networks or high energy efficient networks that can do this initial task of VAD and keyword spotting. Okay, so here we have the pipeline. We have someone saying something, maybe the keyword. We have a module that extracts the features from the speech that comes in. Then we have a network that's trained on these 3 different tasks, or one of the 3 different tasks. And so in our case here, we have the spiking Cochlea that puts out spikes, and then we have an additional feature extractor block that generates the features that needed to drive this network. Okay, but before we do that, I want to talk about yet another way in which you can reduce the computes, and this is really in the network itself, right? So we talk about the 2 ways where you reduce computes through weight and activation sparsity, but there's yet another way which is also inspired by the brain, and this is by skipping over computes in the temporal domain. This is inspired by the spiking neuron model, and which we also call the delta network. And in this case, you're taking advantage of temporal sparsity. And we believe this is one of the principles that the brain uses. And so let me show you how we do this. So here we have the brain, and if we look at a little piece of the brain, you'll see a set of neurons. And from each of these neurons, if I poke a needle into the intracellular fluid, then you might see a response that looks like this, and these are the spikes coming out from the neuron. And you can make a simple mathematical model where you have a module that receives the spikes, sums up the weighted spikes, and then if the summed value exceeds the threshold, then you put out another spike. And this is known as the spiking network, and there are people, groups, even companies building spiking networks. But what we want to do here is to use the synchronous time stepping network that's been used in many places, and then we do an update of these networks only when needed. And this is what we call also event-driven computing. And so here's the normal way that you update a network, like a synchronous CNN, where you update each layer at a time, right? But in this a new way of updating the network, which we call event-driven, is we look for a way in which we determine that certain neurons are active. We fetch the weights only of the projections of those neurons to other neurons in the upper layer, right? And then we again have a condition that check which neurons are active in this layer, and only the active neurons are allowed to update the neurons in the next layer. And so in this way, we save both in terms of the computes that you have to do and the amount of memory fetches that you have to do. And so here's an animation again to show how this principle works. So here we start with 2 neurons, and the level that you see here indicates the activation level of the neuron. So the higher it is, the closer it is to threshold. And so what I'm going to do here for these 2 neurons, I'm going to put this threshold that I'm going to look at when I compute in the next time step what that activation level is. If the activation level for this neuron in the next time step is higher than the threshold, then this neuron will be activated. And say for this neuron, the activation level in the next time step is below the threshold, then it's not activated. So here we get an activated neuron, and here we get a neuron that's not activated. And so we can now apply this now to a whole layer of neurons where we show the activation level at a particular time step. We put the thresholds on top of this level, and then we compute what the activation level is in the next time step. And for all those neurons where you exceed the threshold, which is this, this, and this, then those neurons are activated. And those are the ones that are then used to update the neurons in the upper layer. Okay. And so we've implemented this delta network idea on an FPGA system and show that you can save up to 10 to 100x amount of computes in the network. And so what we're doing now here is we're combining this delta network implementation with the spiking Cochlea. And so again, here, someone who says, say, possibly a keyword going to Cochlea, generate spikes, we get the features, and then we apply this as inputs to the network. And for an example task over here, so what you're going to show here is a demonstration of how we've hooked up this these 2 systems together, the Cochlea and the delta network. And what we're going to do is we're going to recognize a continuously digits, right? So it's a bit like keyword. So you say 0, 1, 2, 3, 4, 5, 6, 7 to 9. And then what you see here on the screen, so first you see on the left, these are the output spikes of the Cochlea. And on the right, you can see the classes that are detected by the network as it receives the spikes.
1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 0, 0, 5.
So it shows that you can train these networks to receive input spikes. And then what we want to do now is to take these two systems. Yeah. So the Cochlea chip and the delta network that's on the FPGA. And we're going to integrate them into one ASIC, right? And when you do that, then you can make a very small device that burns very little power. In fact, there are different groups that have been doing this over the last few years. And usually this is reported at a conference called the Solid State Circuits Conference, which is highly attended by people from industry and also academia. And this is one of the chips that was reported back in 2019. It's a voice activity detection chip. It uses a front end that's a Cochlea with 8 channels and a binary multi-layer perceptron that comes afterwards. And this whole chip burns only 1 microwatt. So it's extremely small. You can see it's 1.6 millimeter on the side. And if you look at the 5 Rappen Swiss coin, this is 17 millimeter on the side. So the scale-wise, you can see it's extremely small. And you can imagine that one of these ASICs then can go into one of these wearables, right? For example, an earbud or one of the home devices. And also, there are other groups that have been building different types of ASICs or ICs. And so here's the keyword spotting IC, burns 540 nanowatts. So this uses features that are extracted from a sampled output of the microphone and uses a CNN, a convolutional neural network at the back. And this is our latest chip that was just presented a couple of months ago. It's a keyword spotting system. And our feature extracted here are time domain features. We use the delta network or delta recurrent neural network at the back. And the whole system level power is only 10 microwatts, right? And we hope that we can build ASICs with other types of edge audio that can run other edge audio tasks in the future, just to show that you can actually build very high energy efficient systems by using some of the principles that you can derive from the brain. And so if we go back to this this graph that we have here, right? So here we go. So we have the GTX 1080 that if you run it with batch 1, so we look at batch 1 effective throughput, you can see that it drops down by over 100x, same thing for Jetson Nano. And these are 2 other systems that we built, which run on the Delta network principle that you can see go down to the 1 watt power range. So they're heading towards edge domains. And then for our most recent keyword spotting chip, we're actually down in this area called extreme edge, where you're in the milliwatts range. Okay, so what can we think about for the future? Well, there are many different things that are currently appearing on the landscape that people are looking at to see how you can increase even more the energy efficiency of a system that has to solve the complex tasks that you see from humans. Like, so one of them are new types of circuits, emerging memory technology. The other thing is how you can develop energy efficient network learning architectures, because learning is quite important, right? You don't want to take a network that's been trained on the server, deploy it on your device and find that it doesn't work well because it hasn't been trained with, we say, for example, the accent of a particular person in recognizing a keyword. And so you want the device or your edge device to do some form of online learning, yeah, without retraining the whole network again. There's an interesting area that's popping out from this way of doing event-driven computing. This is known as event-based or asynchronous signal processing, because the samples are asynchronous. They're not synchronous samples where you can use Fourier transform in order to create spectrograms and then to solve the task from that on. And so we're looking at algorithms for continual local learning and also ideas of event triggered control, something that you can do with robotic systems. And application domains are edge computing devices used for auditory scene analysis, video monitoring, human machine interfaces, mobile wearable electronics, fast robotics, neuroprosthesis. So if you guys are also interested more in this drone domain, so there's something called EV.net that you can also see on YouTube, a video on YouTube, and where one drone is trying to run away from another drone. It's like a predator-prey problem. Yeah, so it's quite a nice demo. And finally, I'd like to acknowledge the census group, in particular Toby Delbrook, the other co-director of the group, also Kwante Kim and Cheng Gao, who both together developed the keyword spotting chip, and also Cheng, who developed a lot of the initial hardware for the Delta network and also put together this continuous digit recognition demo that you just saw. Okay, and finally, we'd like to thank again for your attention, also the Institute of Advanced Studies for inviting me for this event.